Hello everyone, today in this video we are going to see the theorem, that is Rolle's mean value theorem. If f is mapping from a comma b to r such that it should satisfy all these three conditions. First condition is f is continuous on closed interval a comma b. Second condition is f is derivable on open interval a comma b. And the third condition is f of a equals to b. Then there exists C belongs to AB such that f dash of C equals to 0. We'll quickly move into the geometrical representation for this and then we'll move into the proof. So the geometrical interpretation says there are three conditions of Rolle's theorem. The first one is f should be continuous on closed interval a comma b. And the second condition is it should be derivable on open interval a comma b. And the third condition is it should f of a is equals to f of b. Now moving on to the geometrical representation of this, let us have x-axis, y-axis, x-axis. This is origin. So as we are talking about only a and b, first we have to have point A and then we have to have point B. As we are talking about only point A and point B, it should not cross A, either it should not cross B. So now f is continuous on AB. What is continuous? The graph should be in such a way that it should not have any breaks. So the graph, I'm drawing it from here to here. So this is a continuous graph. So f is continuous on closed interval a comma b. And next, f is derivable. What is derivable? Whenever you have a graph, like if the graph cuts like this is not derivable. If a graph is tangent to the curve that is opposite to x-axis, then this is derivable on open interval AB. Why are we taking open interval? Because it is derivable. It cannot be derivable on closed interval. So it will be derivable on the open interval A and B. So this point, I'm just drawing a line over here. And this point will be A comma f of A. And this point will be B comma f of B. And this is a tangent of the curve that is parallel to the x-axis. So what will be the geometric representation be? Geometric representation is, from this curve, what is that we have observed? Obviously, f is continuous on a comma b. It is continuous on the closed interval a comma b. And what is the second condition? That is, it is satisfying f is derivable on open interval a comma b. And there exists a unique tangent. This tangent is unique. There's only one tangent. So there exists a unique tangent. Curve for every intermediate point. That is, this is point A and this is point B. So from in this point A and point B, there is at least one tangent curve. So there exists a unique tangent curve between A and B. That is the intermediate value between point A, that is A comma f of A, and point B, that is B comma f of B. Okay, on the curve. So there is at least one point C between A and B in such a way that f dash of C is equals to 0. That is, if you take the derivative of this point, so this f dash of C will be equals to 0. I repeat this point. F is continuous on A comma B. F is derivable on A comma B. And there exists a unique tangent curve for every intermediate point A and B. If f is derivable on AB, then there exists some point C of C comma f of C such that f dash of C is equals to 0. I think I'm clear with the geometric representation. Now moving on to the proof of the Rolle's theorem. Yeah. Rolle's mean value theorem. If f is mapping from a comma b to r such that f is continuous on a comma b, F is derivable on A comma B, f of A equals to f of B, then there exists C belongs to AB such that its derivative is equals to 0. Moving on to the proof. So first, what is that they gave? We have to consider f is continuous on closed interval A comma B. This implies, as we have already studied earlier, every continuous function is bounded. From that, we can write f is bounded on closed interval A comma B. And now we have to choose capital M and small m in such a way that this capital M is equals to supremum of f of x. This capital F equals to supremum of f of x such that x belongs to closed interval A comma B. And small m is equals to infimum of f of x such that x belongs to closed interval A comma B. So why are we taking this is because we just have to prove the third condition. So I repeat the proof again. Given f is continuous on A comma B implies f is bounded because every continuous function or every continuous function is bounded. By this statement, we can tell that f is bounded on AB. Now I'm just taking this, we are just considering this, that is m equals to supremum of f of x such that x belongs to AB, and m equals to infimum such that f of x where x belongs to A comma B. Now there exists some constant CD such that this belongs to A comma B. Okay, such that f of C is equals to capital M and f of D is equals to small m. Here we have to either consider capital M is equals to small m or capital M is not equals to small m. So in case 1, what I wanted to take is this m is equals to m. What do you think if m is equals to m? Obviously, there is only one way. If these both are equal, f of x will obviously be a constant. Therefore, if m is equals to m, f of x is constant function. So from this, what is that you can write? F of x is equals to k for all x belongs to closed interval A comma B, where k is a constant. If you take the derivative of f of x, f dash of x will be equals to strictly 0 for all x belongs to A comma B. So what is that we took? We took m is equals to m. This is the case 1 we took. If m is equals to m, f of x will be the constant function. And if f of x is equals to k for all x belongs to A comma B, where k is a constant, what will be its derivative? Constant's derivative obviously equals to 0. So f dash of x is equals to 0 for all x belongs to A comma B. From here, we can write f dash of C is equals to 0 for all C belongs to A comma B. Now we will move on to the second case, that is m is not equals to m. Yeah, see here we have f dash of x equals to 0 for all x belongs to A comma B. Then that implies f dash of x, C equals to 0. Now moving on to the case 2. What is the case 2? We have to assume m is not equals to m. That is, what is the condition 3? F of A is equals to f of B. So now here we should either assume f of A is not equals to the capital M. That means as these both are equal, we will get this one. F of B is not equals to m. And same with the infimum case. So now let us consider this f of this one. Now let us consider f of A is not equals to m and f of B is not equals to m. So we get, and we have to assume f of A is not equals to f of C. F of B is also not equals to f of C. From this condition, we can take as f of A is not equals to f of C, we can write A is not equals to C. And as f of B is not equals to f of C, we can write B is also not equals to C. But what is the condition that we actually have? C belongs to closed interval a comma b. But we have to get an open interval a comma b, because the tangent line, like when I was talking about the derivative, that will never be a closed point. So this cannot be a closed one. So that is the reason C belongs to open interval a comma b. Now we have to show that f dash of C is equals to 0 from the third condition. What is that we are actually proving? We are proving that for every intermediate value, there exists at least one C such that f dash of C equals to 0. So that is what we are proving over, that is what we are proving over here. That is f dash of C equals to 0. Oh, 1 second. F dash of C equals to 0. So to prove f dash of C equals to 0, what is that we have to assume first? If possible, we will assume f dash of C is less than 0. And we will prove a contradiction for that. So if f dash of C is less than 0, obviously f is derivable at C. So f dash of C is less than 0. So by locally decreasing at point C, there exists delta greater than 0 such that this f of x is greater than C. This is the definition of locally decreasing function for all x belongs to C minus delta comma C. So, and we have to assume that f of a equals to m, where f of a equals to f of c. What is m? In the previous case, we have assumed m is equals to f of c. So, f of x is greater than m. And for all x belongs to C minus delta comma C, which is a contradiction. Why? Because we have to get f of x is less than m. M is equals to supremum of f of x such that x belongs to AB. Our assumption that f dash of C, which is less than or less than 0, is wrong. So in the same way, we got to prove a greater than. That will also be wrong. So what is the correct statement? F dash of C is equals to 0. So what is that first we took? First, we just took f is continuous and then f is derivable. F of a is equals to f of a equals to f of b. Then there exists C belongs to a comma b. Then we proved that then we had two cases, that is m equals to m and m is not equals to m. For m equals to m, we took f of x is equals to k and its derivability is equals to 0. In case 2, what is that we proved? In case 2, we just took in case 2, we just took m is not equals to m and we proved we just proved f dash of C equals to 0 in case 2. At last, we got a contradiction and we ended up telling f dash of C is equals to 0. Now we will move on to the converse of the theorem. What is the converse of the theorem? The converse of the theorem, the converse of Rolle's theorem states, if f dash of x vanishes at some point C without f of x satisfying all the three conditions, that means the converse need not be true. We'll just look into an example of the converse. We'll just take f of x is equals to 0 when f of x is equals to 0 when 0 is less than or equals to x less than 1 and x plus 1 when 1 is less than x less than or equals to 2. Then, do you think is this continuous? It is from 0 to 1 and 1 to 2. This is not continuous. F is not continuous and it is not derivable also. It is not derivable at x is equals to 1. This implies x is not continuous. X is not continuous on closed interval 0 comma 2 and it is not derivable on open interval. It is not derivable on open interval 0 comma 2. So as these both are not, like these both conditions are not satisfied, obviously what is the third condition? F of a equals to f of b. So f of 0 is not equals to f of 2, but f dash of 0 will be equals to 0 for all x belongs to 0 comma 0 which is 0 comma 1 which is contained in 0 comma 2. So this is the converse of the theorem.